pleasure to announce the last talk of the conference, which is relative monads and their meta-language, and Zev is going to give the talk.
Hi everyone, I'll be talking about the relative monadic metalanguage. This is joint work with Jack Liell-Cock and Sam Staton. So back in the 90s, I was in a very famous TV show, and Eugenio Moggi introduced the notion of a computation type, which has gone on to quite transform the past 30 years of functional programming and allows us to understand effects in a typed way. And in particular, he also gave us terms for given a value, returning a sort of trivial computation that just returns that value, and for sequencing computations. But it's a bit odd, something that's a little odd about the monadic metalanguage, which he introduced, is that even though it doesn't have function types, it's inherently a higher order language because you can iterate T. So the type TTA, which is the type which has of computations which would return computations, well, if you think about what it is in, for example, standard ML, where the monad is just unit to A, it's very explicitly higher order, but it's also has higher order aspects in other settings. And it's not really used for sequencing computations. Also, mathematically, it's often very strange and very difficult to manipulate. So sometimes, I'm not saying that higher order things are bad, right? We've seen a lot of nice higher order effects in this session, but it's nice to separate out the first order aspect from the higher order aspects and study the effect in a first order setting and add in function types and higher order aspects later. So we provide essentially a first order language based on relative monads, which now separates types into two different sorts. So there's ground types, which are types which you can do computations on, and effect types, which are types for modeling computations. So now they're separated into two sorts of kinds of things. And this means you can't iterate T in particular. And we provide a sound and complete semantic. The reason this is called a relative monadic metalanguage is we provide a sound and complete semantics using a new notion of strong relative monads. So relative monads are now quite old and have been very well studied in a variety of categorical settings. And there have been suggested definitions of strong relative monads already, but they don't capture the computational aspects of strong relative monads. So we provide a new definition which subsumes previous definitions and also gives a computational interpretation. So something that's quite interesting about this separation into two sorts is you now have two options if you want to program in an effectful way, right? So previously there was only one sort. We only had one option. You had to program directly with the computation types. And you can still do that. You can still have your programs living in these effect types so that computation types are sort of first-class types that you are writing programs between. And we'll see an example of this in this talk. But what's interesting is we can now do our programming in the ground types and just have access to this extra space of effect types, which we can model computations in and then pull things back. And this means you can model computations in very interesting ways, as we'll see as well in this, later in this talk. So this isn't just a philosophical talk. We have some actual applications in mind. So monads have, over the last 30 years, been taken in all sorts of directions. So they've been generalized, specialized. So for example, arrows are a generalization of monads. I'm going to work right to left. Arrows which model like non-sequential effectful programs. Graded monads model resource usage sensitive effects, so something where you keep track of costs or effect usage. And finitary monads or enriched algebraic presentations of monads give you ways of directly handling a particular effect with extra terms and can be very useful when actually programming with monads. And these can all be unified as particular instances of relative monads, and so can be put in our framework and give very interesting languages for these and many other generalizations of monads. So what is the relative monadic metalanguage? Well, as I said, we separate things out into ground types, which are types that computations can be done on, and effect types, which are types that model computations. We have contexts, which are lists of effect types. And this is pretty important because we want to be able to store computation variables in the context for more expressivity. And we have standard terms for returning a value on a ground type. So J, we have two types of ways of turning ground types into effect types. J just interprets a ground type as an effect type, and T provides computations on the ground type. So given a value of the interpretation of a ground type as an effect type, you can return a computation, which is the do-nothing computation, and we can sequence computations on ground types. And these have to satisfy some equations that mean that sequencing is associative and unital. So as a concrete example, let's turn to programs with randomness. So these are programs that take in some input and with some probability come out without some other output, and often are modeled semantically via stochastic matrices. So rows are non-negative and sum to 1. But these have been known to been modeled monadically via functions from a finite set to distributions on another finite set. So you have this set D of M, whose elements are some weighted distribution, where for each thing you get a non-negative number and they sum to 1. And these are equivalent perspectives. But this finiteness is actually pretty important when it comes to probabilistic programming. So, for example, in the language DICE, which is a finite probabilistic programming language, the inference algorithm requires the space to be a finite type. And if you wanted to have a typed finite probabilistic programming language, this D of N is not finite anymore. It's a different sort of type for programming. You have to treat them differently, especially when it comes to these inference algorithms. Furthermore, while it's possible to define an iterated D, it's not really a useful mathematical object. So there are distributions on distributions that are studied in probability and statistics. The famous Dirichlet distribution is one such. But this doesn't appear in the set. I mean, you have to turn into more continuous or measurable settings to find these, and they have their own problems for semantics. So we want to model the actual restriction to finiteness, so we do probability in the relative monadic metalanguage. So now the ground types are going to be finite sets, and we add in an additional term called coin, which represents a fair coin flip, which returns true with half probability and false with half probability. And then in this language, we can start to write equations, right? So the first equation says that if you flip a coin and you do nothing with the result, that's the same as just the result in the first place. The second equation says if you flip 2 coins, then it doesn't matter which order you use the results of these 2 coins. And the last equation says that the coin is actually fair, so if you flip a coin, then you can use the true or the false as your output. So these are famous equations. They're known as Stone's equations for barycentric algebras, and they can be written in the relative monadic metalanguage. And these equations, alongside the monad equations, so associativity and a unitality of sequencing, provides a complete axiomatization of this model of finite stochastic matrices if you restrict to dyadic rationals, but you could obviously make it all stochastic matrices if you added in coins of every bias. But this provides a nice, simple example. And this example is not limited to probability. I showed you probability because it's clear that you need this finiteness understanding, but there's many, many other algebraic presentations that can be done within the relative monadic metalanguage. And we give another example of local state in our paper. And in fact, many of the languages that people have been using in the past were instances of relative monadic metalanguages. Okay, so this gave you an example of the first setting where we're doing the programming in the effect types. Later we'll see an example of an example where we're doing the programming in the ground types. So what's semantically going on? Well, distributions is a functor which takes in a finite set and returns distributions on that finite set. So goes from finite sets to set, because the distributions might be infinite. The interpretation of ground types as effect types is also a functor. It just says a finite set is also a set. But this distributions functor has additional structure for being able to return values on ground types and sequence computations on ground type. And this is known as the structure of a relative monad. So given more generally an interpretation of ground types as effect types and computations on ground types and a way of returning values on ground types and sequencing computations on ground types, this is the definition of a relative monad. So just to make it really clear, I'll put a monad and a relative monad next to each other because many of you are probably more familiar with a monad. So the key differences are a relative monad is a functor from ground types to effect types. It's no longer an endofunctor. It can only return values of a ground type, and it can sequence computations on ground types. And in fact, it should be clear by this comparison that a monad is actually just a relative monad. Sorry for using the word just. When you you set the interpretation to be the identity functor. But actually, it's not enough to just have relative monads because we need context for our programs. We need to write programs with variables, right? And often multiple variables. As you saw in the equation I showed you before with this commuting 2 coins, we needed 2 variables. We needed multiple things in the context. And in programming languages, the way that we have monads with context of variables is using the notion of a strong monad, which allows you to thread context into sequencing effectful programs. So here you have a program which returns a effectful type A, and another program which depends on A but produces something effectful of type B. But it could have other things in the context, right? And we need to provide something from that context effectful of type B. So we need to have a way of sequencing in context, which is this contextual bind operation. So how do we do that for strong relative monads? Exactly the same. We provide a contextual bind operation for sequencing computations on ground types in a context of effect types, because the context may have computation types in them. Otherwise, and then it satisfies some equations, like a strong monad does. So with this new notion of strong relative monad, we can provide a completeness and soundness theorem that says that our language presented before can be interpreted in any Cartesian category with a strong relative monad on it, and also the term category of our calculus. The term model of our calculus is one such example of this. So now to look at the other side of the coin, pun intended, in terms of modeling in the relative monadic metalanguage, we're going to look at an example where all the programming is happening in the ground types, but we have access to these ambient types living in the effect types for a particular type of modeling computations. In this case, we're going to look at graded monads. These are well-known semantic tool for modeling effect usage sensitive computation. So think about cost. That's the analogy I always have in mind. So now for each A, we have a computations of cost M type, TMA. And the relevant terms are also cost sensitive. So if I have a value, the computation that just returns that value, it doesn't do anything, right? So it shouldn't cost anything to do that. And so it's of type identity cost computations on A. But if I have an M cost computation and an N cost computation, and I sequence them, I run the M cost computation, I feed it into the N cost computation, the resulting computation should be of cost M plus N. So this is graded by a monoidal category in order to capture this addition and unit costs. One thing to note here is that M is an explicit parameter, external parameter of our language. However, not in the wrong slide, sorry. There's an example of list, which is a very famous example of a graded monad, which is graded by number of choices. So list model is non-determinism. At each point, I can branch in many ways. And a natural way of thinking about costs of branching is how many branches do I have to investigate, right? Like, do I if I branch 2, then that's a lot more work than branching just one. So here we have a function which outputs 2 things, and then we have a function that outputs 3 things. And you can see that the composite can output at most 6 things, and so it's graded by naturals with multiplication. We can model graded monads in the relative monadic metalanguage by adding explicit grade types first class into the language and model them linearly. So now we have ground types, which is just the simply typed lambda calculus, right? So it has products and exponents. And we have effect types, which is the linear lambda calculus. It's going to be modeled linearly because grades track resources, so should be modeled linearly. And then we add in a linear-nonlinear adjunction. So we have a way of turning effect types back into ground types and producing effect types from ground types. And all we do on top of Benton's linear-nonlinear calculus is add on a relative monad. So with this relative monad and first-class grade types, we can model graded monads. And the fact that they're first class is really important for multiple reasons. You recall that in the previous version, it was an external parameter of the language. So firstly, they're modeled in the calculus as linear, so they actually do respect the resource sensitivity that we want them to. Secondly, it's much more flexible in terms of implementation, right? So we don't have to put in all the grades. We can just construct grades within our language. And it has a lot of reusable code. So the bind, for example, is written exactly the same for all the grades, and so it's one step towards sort of grade polymorphism. So once we have this set up, this relative monadic metalanguage, which has linear effect types, we can write a graded monad on the ground types as such, and then we start to see the real advantages of having a linear part and a nonlinear part to this language. So having nonlinear ground types allows you to program as normal if you wanted to write any sort of graded effectful program that you want. So say you have a program from A to A, which is effectful of cost m, right? You want to be able to sequence this with itself, right? That relies on nonlinearity because it relies on duplicating it, and the duplicating term should cost m plus m because you sequence it with yourself. So here I've written a sort of nonlinear function which duplicates f and sequences it with itself. But the linearity of the E-types is also really important for enforcing this cost of computation. So here we have a program that will run a computation of cost m on A and run a cost of computation of cost m on B and return both outputs. That should cost m plus m, but if this E-type was modeled non-linearly, we could feed in the m variable twice into the computation, and then the resulting computation would only cost m. So it is actually a very important condition. So we have now 2 languages for graded monads. How do they relate? Well, this language for graded monads with just explicit, everything is externally imposed in order to provide a language for graded monads, embeds into our calculus because we have a graded monad on ours, and this is a conservative embedding, so we can't prove any more equalities between terms in our language than in the traditional language for graded monads, which everything is externally imposed. How do we prove this? Well, it's quite tricky, but first step is you take a graded monadic metalanguage model, that's a Cartesian category with a strong graded monad on it, and you take presheaves on it. And presheaves is now going to be a Cartesian closed category with all limits and co-limits. And so you can show that this is part of a linear-nonlinear model, which consists of, in this case, E hat valued, but here I wrote E because a different E, maybe I should have made that clearer. So if you have a Cartesian closed category with all limits and colimits, then this provides a linear nonlinear model. And we saw before that when you have a linear nonlinear model and a strong relative monad on it, you obtain a graded monad, but that was one way. In this case, because there's loads of limits and colimits, and this is a particular model, you get away the other way around. So if you have a graded monad, you can construct a relative monad. So this shows that every graded monadic metalanguage model embeds into a model for our calculus, and it embeds fully faithfully, and that proves conservativity. So if there's one slogan that I want you to take away from this talk, it's that relative monads allow you to control computation, right, in two different ways. And we saw both sides of the coin in this talk. So first, you could do your programs in the effect types, and then ground types control where computations take place. So for example, if you want to have a typed finite probabilistic programming language, you can put finiteness guarantees on the thing that you're running computations on. But you could also have your programs living in the ground types, and then effect types control how computations are modeled. So we saw one example here where the effect types are modeled linearly, and then we can have a linear usage of effects, and so model graded monads. But what are the full contributions of our paper? Well, we provided a framework metalanguage with complete semantics via a new notion of strong relative monads. We provided a first-order syntax for enriched algebraic theories in this setting. And we provided a new language for both graded monads and for arrows via our framework, and proved conservative extension theorems for both of them, which extend the previous known calculi for graded monads and arrows. Thank you. That's
beautiful, I think. So any questions? Yeah.
What about relative graded monads?
Yeah, that would be quite interesting. I don't know if it would fit into this particular language, but it's definitely something that would be interesting to see whether you could extend it in that way. I mean, something that we did note is that having this relative monadic framework for example, graded monads, gives you a better semantic understanding of how to extend things, so how to add in additional language features. It seems easier in our framework.
And are graded relative monads different than relative graded monads? Okay, you don't have to answer that.
Right. Any more questions? Yeah.
Hi, great talk, really interesting work, and I'm trying to stitch together what the parts are on here. So you introduced, you pulled in linear and nonlinear and this kind of adjoint model because you wanted to have things treated linearly, but that adjoint model of two categories and that connection between them is, in fact, that kind of doesn't really have to relate to linearity at all and is collected to kind of call by push value and other constructions. So it is, in fact, your relative monad construction an instance of this adjoint calculus in the first place?
Thanks. Yeah, so there's a lot of interesting connections to call by push value. Certainly, in the sort of primitive framework model, there's no way to get back into the ground types, and so you do need to add an adjunction if you want to do your programming entirely in the ground types. And as you say, a linear nonlinear model is in particular a call by push value model, and so the question is whether this can be viewed as built on top of call by push value in some way. There is another work which, ordinarily you can't necessarily force computations here, which it makes it slightly weaker than call by push value. There is another work that Max Nu and others have looked at where you add a relative monad on top of call by push value, which looks like, well, it doesn't have strength, which is a little different from how we approach things. So there they rely on the sort of unary stat context to work with ordinary relative monads, at least as far as I understand that work. But there's definitely interesting connections that we would like to.
Okay. So I mean, in some sense, yes, what you have things are. In some ways, these are weaker than other models of these things because you can't. You want to have this separation. You can't necessarily get forced computation.
Yeah.
Something's very.
Yeah.
But it seems to be moving towards something in a kind of a la carte thing of you want this combination of features. Then what you have is a relative model or something that's called population value or linear nonlinear, and they're all shades of similar structures. But you just need to be explicit about which of these features, which are clearly delineated, do you want in your system.
Yeah, I think so. I think semantically, a relative monad looks very different to a sort of a call by push value model, but they can be sort of melded together in interesting ways, I think.
Right. Thank you.
Time for one more question, maybe. Yeah.
Thanks for the talk. You showed this example where you defined you had this R of M lolly. Maybe if it's possible to go back to that. Yeah, this graded monad. That looks a lot like a graded adjunction. Is this something you've thought about, maybe in line with the previous question?
In the sense that this is a sort of graded reader monad, or?
Well, I'm just thinking maybe you have, I think as far as I understand, a graded adjunction consists of a J and maybe an R and a T, at least in some formulations, and maybe this looks kind of like call by push value, where R is the right adjoint and T is the left graded adjoint. Have you thought about something like this?
I mean, this is, in particular, a sort of like built on a call by push value kind of thing. But there is, the relative monad is playing a very important part in the definition of this. So this relative monad built on top of it is pretty critical.
All right, so I think we should take further questions for the coffee break. So thanks, Seth, and everyone.